Hello, and welcome to Slice of Physics. I'm going to be talking about energy in capacitors, in particular how capacitors can be used to store energy. First of all, let's see that it requires energy to charge up a capacitor. So, if I have a capacitor here, and let's say that it's already charged to some extent, and I want to charge it up further. So I want to put more charge on it. So to do that, I will hook it up to a battery, and I will make the battery push electrons from the plate on the left to the plate on the right. So if I move one electron from the left side, that will leave a positive charge behind, and then it will come around to the right side, and it will appear on the rightmost plate. So charging up the capacitor like that requires energy, because it requires work. So these positive charges, the negative charges on the left plate, if I take a negative, so here's a negative charge and it has a positive charge. It likes being there. It likes being attached to this positive charge. So then it's going to move around the circuit and end up on the rightmost plate. So it's being taken from a place that has lots of positive charges and being put on a place that has lots of negative charges. So that's going to require energy because it doesn't want to do that. So how much energy is required? Well, if I move a charge of size Q from the left plate to the right plate, then the energy required is equal to the charge that I move times the potential difference that I move it through. Now this energy is stored in the capacitor, and it could be released if I were to allow the electrons to move back through the wire. Let's say I got rid of the battery and I just allowed them to run back through the wire to the other plate where they want to be. Then it's like allowing them to roll down the energy hill or up the potential hill until they get to the other plate. So in doing that, I could allow some energy to be released. So let's think about how much energy can be stored on a capacitor when I hook it up to a certain battery. So as I have this, let's say I have this capacitor and it's completely uncharged. The first electron, let's say I move one electron from the left-hand side to the right-hand side. So this electron really doesn't care about my doing that because there's almost no charge on this left-hand plate or right-hand plate, so it's like moving it from one place on the conductor to the other. This electron really has no preference about where it's going to be. It's only when I start to get more and more charges that the electrons start to say, wait a minute, I want to be on the left-hand plate with all the positive charges. So as I start to add more and more charges, then it requires more and more energy, and the potential across the plates becomes larger. So at the start, the delta V across the plates is 0 because there's no charge on the plates. And in the end, there's some maximum potential, which is the battery, right? The battery's potential difference is what determines the final potential difference. So when I have this equation that the energy required to do this should equal the charge on the capacitors times delta V. But what delta V should I use? Well, I shouldn't use 0, obviously, and I also shouldn't use the maximum potential across in other words, the battery voltage either, because it's actually, the truth is somewhere in between. So what I should actually use is delta U to charge up the capacitor is Q delta V max over 2. So I'm using half of the maximum potential difference, which is an average. And that tells me the energy that's required to charge up the capacitor. So we also know that the maximum potential difference that we reach when we fully charge the capacitor is equal to the charge divided by the capacitance, and that's because the capacitance is the charge divided by delta V. I'm going to use delta V now instead of delta V max, and I'll just assume that delta V means the final potential difference across the capacitor. So this is delta V max. I'm just going to write delta V for it. So that means that the energy that we've calculated is 1/2 C, sorry, 1/2 Q delta V equals 1/2 Q times Q over C equals 1/2 Q squared over C. So that's the energy stored on a capacitor. Another thing we can do is we can say that Q equals C delta V, and that means that delta U equals 1/2 C delta V times delta V equals 1/2 C delta V squared. So this formula also tells me the amount of energy that's stored on the capacitor. Okay, so let's apply this. Let's say that I have a defibrillator, and the capacitance of this defibrillator is 60 times 10 to the minus 6. What are the units of this capacitor? The unit is called a farad. It is just 1 farad. Farad equals 1 coulomb per volt. In other words, if you had a 1 farad capacitor, then each volt of battery that you applied to it would store 1 coulomb of charge. So let's say that I also put 3,000 volts across this defibrillator, and I want to know how much energy will it store. Well, we know that the energy stored equals 1/2 C delta V squared equals 1/2 times 60 times 10 to the minus 6 farads times 3,000 volts squared equals 270 joules. So that's the amount of energy that would go through someone's body if this capacitor were discharged into them, and maybe that would all go through their body in 1,000th of a second or a millisecond, which is pretty fast for 270 joules of energy to go through you. Okay. So in this lesson we learned about the energy stored in a capacitor. We also learned about two formulas for counting the energy stored in a capacitor. We have U equals 1/2 C delta V squared, and the other formula that is equivalent to it is 1/2 Q squared over C.